Good morning, everyone. My name is Yu Chuang. Today's report is about my work published in ICCV 2025. The title is From Easy to Hard, Progressive Active Learning Framework for Infrared Small Target Detection with Single-Point Supervision. I will introduce the following four aspects. Firstly, I will introduce the research background. Single-frame infrared small target, SIRST, detection is one of the key technologies in infrared search and tracking systems, and has been widely applied in maritime rescue, early warning systems, ETA. However, due to the small size of targets, lack of intrinsic features, and severe interference, achieving high precision detection remains extremely challenging. At present, most existing SIRST detection methods rely on full supervision, which requires costly pixel-level dense annotations. Consequently, search detection with single-point supervision has attracted increasing attention. Nevertheless, the latest approaches that directly evolve from all-point labels suffer from instability, excessive label evolution, and difficulty in leveraging the embedded network potential. To address these issues, we attempt to construct a novel, efficient, and stable framework for SIRST detection. Next, I will introduce our method. Inspired by organisms gradually adapting to their environment and continuously accumulating knowledge, we came up with an idea: the learning of network models should also be from easy to hard. We believe that an excellent learning process should be from easy to hard and take into account the learning ability of the current learner rather than directly treating all tasks equally. We call it progressive active learning. Its abbreviation is PAL. How can we enable the model to simulate this process? We considered whether it could be designed by mimicking the stages of human learning. This process can be roughly divided into four stages: the infant stage, the child stage, the graduate student stage, and the expert stage. In this progression, the roles of mothers and teachers are also crucial in guiding the transitions between stages. Specifically, an initial model can be regarded as a newborn baby. At this stage, the role of a mother is not to immediately teach the baby complex theories such as quantum mechanics, but rather to consciously impart simple abilities such as basic language expression and logical thinking. Similarly, by filtering and allowing the model to learn from easy samples in its early stage, it can acquire the fundamental skills for the specific task and gradually evolve into a student model. For the student model, it begins to develop plans for the future and strive toward them. During this process, equipped with basic skills and under the guidance of a teacher, the model can assess the difficulty of tasks it faces and progressively learn from easy to hard, thereby continuously enhancing its own ability. Based on this idea, after pre-start, the model actively identifies and gradually learns more difficult samples, while the teacher appropriately increases task difficulty to stimulate potential, and pseudo-label biases are corrected through periodic updates. After multiple rounds of reinforcement, the model then resembles a graduate student, with strong cognitive and learning abilities and a comprehensive learning of knowledge. However, to eventually become an expert, it must refine its knowledge and achieve proficiency in practical application. To this end, we periodically update pseudo-labels in the training pool, enabling the model to sufficiently learn from all samples and achieve comprehensive and robust detection capabilities. Based on the above ideas, we propose a progressive active learning framework. The proposed PAL framework couples internal self-learning with external guidance to realize progressive learning from easy to hard. Our PAL framework consists of three phases: model pre-start, model enhancement, and model refinement. The model pre-start phase aims to give model the initial task-specific learning ability. Like a newborn, an untrained model has potential but requires simple knowledge first. This is why existing methods that directly use all samples with point labels for training have problems such as unstable training and poor accuracy. Additionally, low-performance models may misidentify hard samples, thereby compromising final performance. Inspired by early maternal guidance, we construct an easy sample pseudo-label generation (EPG) strategy to automatically generate pseudo-labels for all samples. and divide them into easy samples and hard samples according to the quality of pseudo-labels. Only easy samples enter the training pool for training with a fixed epochs. The model enhancement phase aims to make the model progressively and actively recognize and learn harder samples to ensure the accumulation of new knowledge, and to update the pseudo-labels of samples in the training pool. Specifically, the model evaluates hard samples in the preparation pool, transferring those with reliable pseudo-labels to the training pool through periodic course outer updates. Simultaneously, all pseudo-labels in the training pool are iteratively refined via fine inner updates. It is like students adjusting their misperceptions of acquired information as their abilities grow. In addition, inspired by teacher-guided learning, we introduce additional guidance to dynamically adjust the difficulty threshold based on the model's capabilities, accelerating learning and ensuring that the to-be-learned content is learned in a timely manner. The model refinement phase aims to allow the model to fully learn hard samples and further refine pseudo-labels. Specifically, the hard samples are periodically and gradually added to the training pool in the model enhancement phase. For hard samples that enter later, it is difficult to be fully learned in a few periods. At the same time, as the model continues to learn hard samples, its stronger detection ability can help further refine the pseudo-labels. Therefore, we perform the fine inner updates periodically. This phase resembles graduates refining their expertise through repeated review and practice to achieve proficiency, compared to directly training with point labels. Selecting easy samples that can generate high-quality pseudo-labels for initial training can help the network establish basic SIRST detection capabilities. Therefore, different from existing methods, we propose a model pre-start concept and propose an EPG strategy. To reduce background interference, we process local image patches centered on the given point label instead of the entire image. To accurately detect the target area, we first use the Gaussian filtering to appropriately suppress the noise. Second, the Canny operator is used to extract the target's contour. Finally, a morphological closing operation mitigates contour fragmentation and fills the enclosed area to obtain the segmentation result. To select easy samples and refine pseudo-labels, we make full use of the point labels and the segmentation results. First, the given point label is used to assess connected areas in the segmentation result. Areas containing the label point and below a set threshold are identified as true targets, while others are removed as false detections. Second, we calculate the target level recall rate, which is the proportion of real targets that are correctly detected. If it is greater than and equal to the set threshold, it is regarded as an easy sample. Otherwise, it is a hard sample. Third, each segmented image patch of the easy sample is added to a pure black background with the original image size to generate a pseudo-label. Finally, point labels are added to compensate for missed targets, thereby refining the pseudo-labels. The proposed EPG strategy selects easy samples with high-quality pseudo-labels for initial training, enabling the model to develop basic task-specific capabilities. This also prevents hard samples from introducing excessive noise or misleading information during the early training phase. This page shows the label evolution results of MSDANet equipped with the previous LESPS framework. It can be found that as the number of epochs increases, the labeled area expands excessively and does not shrink, which will affect the final detection performance. Therefore, unlike existing frameworks that directly iteratively evolve all point labels, we propose a fine dual update strategy, consisting of a course outer updates and a fine inner updates. The course outer updates, COU, are intended to continuously and actively learn more difficult samples. After the model pre-start phase, the model has basic SIRST detection capabilities. Based on it, we assess the remaining hard samples in the preparation pool to select easy samples whose generated pseudo-labels meet the selection rules into the training pool. The COU can be divided into 3 steps: determining recognizable samples, eliminating false targets, and supplementing missed targets. First, we assess hard samples in the preparation pool that the current model can recognize. Second, the selected easy samples undergo false target elimination. Specifically, Predicted target areas that do not intersect with any true point label are directly removed. Finally, the ground truth point labels are incorporated to mitigate missed targets and ensure effective learning. Considering that the model will have stronger cognitive and learning abilities after learning hard samples, we periodically perform course outer updates during the model enhancement phase. This drives the model to progressively and actively recognize and learn more harder samples without catastrophically forgetting easy samples. Fine inner updates, FIU, aim to continuously perform fine updates on pseudo-labels. Fine inner updates can be divided into 3 steps: candidate area extraction, false area elimination, and pseudo-label update. For candidate area extraction, we first obtain the binary label for the nth pseudo-label iteration. Second, the centroid of each target connected area in the pseudo-label is extracted and the corresponding d times d local area in the pseudo-label and prediction result is cropped. Finally, to highlight the target area and reduce accumulated errors, we use adaptive thresholding to extract the local candidate areas from the prediction results. For false area elimination, we use the centroid of the target area in the pseudo-label to check for intersections with the candidate areas. Candidate areas without intersections are eliminated. For pseudo-label update, we first restore the positions of all refined candidate areas and use the maximum method to combine them into complete candidate areas. Among them, we introduce a decay factor to help achieve a dynamic balance between the expansion and contraction of target annotations. With the improvement of model capabilities and various constraints, the evolution of the target annotation area achieves a dynamic balance between expansion and contraction and generates more refined pseudo-labels. For the SIRST detection task, the lack of intrinsic features makes it difficult to accurately locate the target area. Therefore, we introduce an edge-enhanced difficulty mining, EEDM, loss to guide network optimization. This helps alleviate the imbalance problem of positive and negative pixels, and directs the model's focus to edges and difficult pixels during training. Specifically, EDM loss emphasizes pixel-level fine-grained detection, which consists of 2 parts, edge pixel enhancement and difficult pixel mining. On the one hand, the edge pixel enhancement increases the focus on edge details by weighting the loss of edge pixels, thereby enhancing the model's learning of important features. On the other hand, the difficult pixel mining helps the model better focus on difficult to detect target areas by filtering pixels with larger loss, thereby promoting the model's learning in complex areas and preventing small targets from being submerged by the background. Next, I will introduce the experiments. To validate our proposed PAL framework, we conducted extensive experiments on multiple public datasets. The figure on the right shows our experimental results on the SIRST3 dataset. First, the curve trend of CNNs equipped with the PAL framework is basically consistent with that of full supervision, whereas CNNs with the LESPS framework is not. Second, CNNs equipped with our PAL framework can achieve 79, 33%-86, 93% and 97, 82% to 100% of their fully supervised performance in terms of the IOU and PD. Finally, compared with the LESPS, using our PAL framework can improve by 8, 53%-29, 1% and 1.07%-12, 3% in the IOU and PD. In summary, our PAL framework achieves significantly better results and can build an efficient and stable bridge between full supervision and single-point supervision tasks. This page presents a detailed comparison of the results of different methods on the rich SRST3 dataset. Our PAL framework demonstrates stable performance and outperforms the LESPS framework in all cases. This demonstrates the excellent generalization and robustness of the proposed PAL framework across multiple scenarios and target types. This page shows the comparison of different methods on 3 other separate datasets. The PAL consistently outperforms the LESPS with notably higher stability. These show that our PAL framework can solve the single-point supervised SIRST detection task with few training samples, whereas the LESPS framework suffers from a high risk of failure. Specifically, compared with the LESPS, using the PAL framework improves the IOU by 7, 41%-57, 28%, the NIOU by 8, 36%-62, 37%, and the PD by 0, 76%-70, 72%. This page shows a qualitative analysis on some difficult samples, where CNNs equipped with our PAL have target-level detection effects similar to those of full supervision, and they are significantly better than the LESPS. To fully validate the proposed PAL framework, we performed detailed ablation experiments to verify and explore the effectiveness of each component and the stability of hyperparameters. For details, please see our paper. This experiment needs to be highlighted. In the table, MP denotes the proposed model prestart. MP1 and MP2 denote the model prestart with all samples initially enter the training pool by setting the target recall threshold to 0 and directly carry the true point labels for remaining hard samples into the training pool. From S1 S6, it verifies the effectiveness of our model prestart concept of learning only easy samples in the initial phase. It's like babies should be given pronunciation exercises rather than forced to learn calculus. From S4 and S7, compared to using only easy samples, gradually selecting hard samples into the training pool based on the current capabilities will again achieve significant performance improvements. Finally, we summarize our work. Inspired by organisms gradually adapting to their environment and continuously accumulating knowledge, we construct an innovative PAL framework that can transfer existing SIRST detection networks to single-point supervision tasks and drive them to progressively and actively learn harder samples, thereby achieving continuous performance improvements. We hope that our study can draw attention to the research on weakly supervised SIRST detection. Our code has been open sourced and everyone is welcome to use it.